Okay, this is Journey to Better Health lecture. We're on part 4. And I'm just going to start out showing you a curve after eating different foods. If you eat a really sweet drink with no fiber, it all hits the gut absorption, as a bolus. You'll get a spike in your blood glucose, and the pancreas will often overcompensate, release too much insulin. Your blood glucose will come down quite rapidly. That's called rebound hypoglycemia. The person often responds by ingesting something else that's very sweet, and their blood glucose curve goes up and down, like a roller coaster. That can lead to weight gain. That can lead to erratic behavior. People, I know what it is. So if I were to sense rebound hypoglycemia, I'd real quickly drink something like beet juice or something, okay, and I'd be fine. But people who don't know what it is, they can become very confused and very agitated, and they can actually behave very badly. That's a lot of bad behavior is related to that. So it's important to figure it out. The next thing is, if you eat high-fat foods to start with, that'll cause insulin resistance. And then if that is followed by carbohydrates, then you get a real high, prolonged, elevated blood glucose when you eat the carbohydrates, because the fat had caused the insulin resistance, and then the carbohydrates that come after that you won't be able to get that blood glucose into the skeletal muscle quickly, so you'll have a prolonged postprandial, prandial means eating, postprandial hyperglycemia. Okay, but the problem was the fat, not the carbohydrate. The best foods are for satisfying hunger are starch is the best, then fruits. Okay, with the starch, you'll get a little bit of spike in your glucose. You're supposed to get a little bit of a spike in your glucose, but it won't go too high, and it'll stay relatively normal a prolonged amount of time. You're in the Goldilocks zone, the golden mean, where you want to be. Satisfying hunger with the fewest number of calories, prolonged satisfaction of hunger, and you'll probably have an optimal body weight or close to it. Okay, a little bit about the Windkessel effect. The Windkessel effect relates to the ascending thoracic aorta. So right when you come off the left ventricle of the heart, the ascending thoracic aorta is the first blood vessel that receives the contraction of the heart. And it initially is distended outward, but it has a lot of elastic fibers in its wall. So during diastole, cardiac relaxation, the ascending thoracic aorta will have elastic recoil and shrink its diameter, come inward, and that pushes blood during diastole. So the top number in the blood pressure is the systolic number. Systole means contraction in Greek, so it's left cardiac contraction, the high number. Then the number underneath the line, or the lower number, is the diastolic number. So like 110 over 70 would be a very good blood pressure. And what happens, though, is a lot of people are chronically hypertensive, and they destroy these elastic fibers, and then they can't generate that good of a diastolic pressure, and they'll get a wide pulse pressure. Pulse pressure is the subtraction of the top number minus the bottom number. So 110 minus 70 equals 40. So here's somebody with hypertension, 200 over 100. Their pulse pressure would be quite wide. 100 is the difference between the top number and the bottom number. Okay. This is also why, as people have been hypertensive for a couple decades, by the time they're, let's say, 50 years of age, then they've destroyed their elastic fibers. You can't get them back after you're in your 20s, after you're done with growth, maturation. So what happens is you just can't generate good diastolic flow, and to compensate for that, you'll have increased systolic pressure. You'll have chronic systolic hypertension often the rest of your life. You can improve things with improving your diet, but the longer it goes on that you're hypertensive, the more likely you're going to keep getting reversible damage. You also get, in the walls of your arteries, when you're hypertensive, you get initially a reversible process of hypertrophy of the smooth muscle cells. They get thicker and more of them, okay, but that's reversible. The longer you're hypertensive, the more you start developing irreversible things like, collagen being laid down in the arterial wall due to the hypertension itself. And so you get fibrosis of the arterial walls. Arterial sclerosis, fibrosis, kind of the same thing, and that's hardening of the arteries. Okay. In addition, if you're chronically diabetic, you'll get glycation, your basement membrane, and you'll get thickening of your basement membrane, which also makes the arteries less flexible, more like a fixed rigid pipe than an elastic structure in response to its environment. Okay. And Windkessel refers to the thing that looks like a little accordion that you blow air on the kindling within a fire to kind of get the fire going. So it's called the Windkessel effect. And you lose that if you're chronically hypertensive for a couple decades. And usually you don't start getting bad atherosclerosis, like in your carotid and other stuff, until you've lost the Windkessel effect. And you're less able to perfuse your heart, your coronary arteries, because you have less diastolic flow. Coronary artery flow is primarily during diastole because the muscle's contracted during systole and you can't get blood into the muscle itself, except when it's relaxed. And then if you got lousy diastolic pressure, it's going to be harder for you to fill your coronary arteries, your epicardial coronaries, and the rest of them. Okay, here's a book about Walter Kempner and the rice diet. It was written by Barbara Newberg. She is a doctor who worked with him. So hands-on, inside scoop. It's a very good book. I recommend you read it. Kempner is one of the all-time greatest doctors that lived. I'd probably put McDougall number one, him number two, are the two best doctors who ever lived. Okay, he basically cured all these chronic diseases with a rice and fruit diet. McDougall called him the father of dietary therapy. Now, one thing a little interesting is, let me just get into a little bit about how this sodium, potassium, calcium stuff works. In every cell in your body, at least 25% of the energy goes to this pump, the potassium-sodium pump. K is for kalium, the Latin word for potassium. N is for natrium, the Latin word for sodium. And it requires ATP. The reason it requires ATP is you can think of all life as, let's say, originally originating in the sea. And the sea is full of salt water. And then something formed a little membrane around itself. God planned it all. But it had to get the salt out because you have to be isoosmotic with the extracellular matrix or the cell would pop. So in order to get anything else in that cell besides sodium, you have to pump sodium out. Okay, so now you pump sodium out. And then you can have other things in there. And by the way, the total amount of sodium and potassium in a cell is always constant. It's always the same thing. And what that means is if sodium goes up, potassium has to come down. If potassium goes up, sodium has to come down. It's always constant. You need to know that. Okay. Now, our ancestors ate tons of potassium, not much sodium. So our kidneys are designed to excrete potassium and to conserve sodium. Okay, but in terms of generating a membrane potential, the voltage across this membrane is negative 65 millivolts. And it's produced by the sodium-potassium ATP pump functioning as an electrical generator. So like in an electrical generator, it has a charge barrier here, which is a plasma membrane. And you're pumping more positive charge out, 3 sodiums out and 2 potassiums in. So you have a net negative charge inside the plasma membrane. All right, that creates an electrical gradient whereby the positively charged sodium wants to come into the cell. And you also have a concentration gradient. Sodium concentration outside the cell is 10 times higher than it is inside the cell. And with potassium, it's the opposite. Potassium is 10 times higher inside the cell than outside the cell. If you look at like sodium in the blood, it's about the same as sodium in the extracellular matrix, about 140. Sodium inside the cell, let's just call it 4 because that number is going to work for us and it's about right. Okay, potassium is going to be about 140 inside the cell and about 4 on the outside. Think of it as being the opposite of sodium. Those numbers are going to work. They're not exact for the potassium, but they work, so just go with them. The exact is close to that, but it's easier to remember it that way. All right. Now, you need magnesium because magnesium holds the second and third phosphate on ATP in place until they're ready to react. Okay, so the point I'm making is you now got this electrochemical gradient, and the electrochemical gradient enables you to do work. It's like a battery. Richard Moore, the guy who wrote the best book ever written about high blood pressure and plasma membrane ion pumps, he calls it the sodium battery. So to have current, you just need flow of a charge. It can be either electrons producing the current as it does in electrical appliances, but inside a cell, current comes from sodium. Sodium is the net charge. If you just had 2 coming in and 2 going out, positive charges, you wouldn't have net current. But you have net current of positive charges flowing out because more sodium goes out than potassium comes in. And now if you had to describe these ions, you could give them a personality. So the potassium and the magnesium are the good guys. They are the middle class trying to hold things together, trying to work together to keep the cell functioning and to keep the person healthy. Now the calcium is sort of the aristocrat ion. It comes in the room and it bosses everybody around and it's not reasonable. It just says, do what I say and do it right now. Okay, so I'd say the calcium is kind of like my wife, my ex-wife. The aristocrat, the boss, comes in. When the calcium gets high in the sodium in the cytoplasm, that's like flicking the on switch. And then whatever that cell does, it will do its thing. So if it's a neuron, it'll release its neurotransmitter. If it's a vascular smooth muscle cell, it'll contract. So you need to remember that calcium is the bossy aristocrat ion, okay? And then sodium is like the angry poor that's living outside the gates of the city. The cell is like the city, and the angry poor want to come into that city, okay? So calcium is basically using the angry poor against the middle class ions, the potassium and the magnesium, okay? That will make sense. So what's happening here now is if you have, imagine I'm like boxing and I'm throwing punches real fast. Boom, 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 okay? I gotta contract, relax, contract, relax, contract, relax. I gotta turn that on and off very fast. It has to be electrical. You can't do something this fast like Macho Camacho unless you have an electrical system generating those instructions and those messages and those movements. It has to be electrical. Okay, so what I'm saying is not only does a cell have to contract fast to do these things, it has to be able to turn off fast. So how are you going to turn off quickly? You've got to be able to pump the calcium ions out of the cell very quickly. This sodium-potassium exchanger, sodium-calcium exchanger called NACA, Na for natrium for the sodium, Ca for calcium exchanger, usually abbreviated NCX. It can pump out thousands, like 4,000 calcium in 1 second. It's incredible, okay? Imagine you ask the best scientists, biochemists, synthetic chemists in the world to make a cell membrane pump that could pump out thousands of calcium ions per second. Good luck. Good luck in achieving that. So it's like a miracle, okay? And this NACA exchanger is, you can think of it like a water mill wheel, or really like a big revolving door in, like, say, a big hotel building or something. So basically, the angry poor, the sodium wants to get in to the cell, and it charges in, and it has such a strong electrochemical gradient coming towards the negative charge, a negative 65 millivolts, and, you know, neutralizing its own gradient of concentration, that it pops the calcium out real fast. Okay, so that's how you can lower the cytoplasm calcium very quickly and turn the cell off. A cell also has to be turned off, so otherwise it would exhaust itself. Okay, but that's a key thing, that concept of the NACA exchanger. And as a matter of fact, the potassium sodium ATP pump, it's the only thing that pumps out sodium. It's the only thing pumping out sodium. And this sodium battery is used to do all kinds of jobs along the plasma membrane, okay? It's also used to pump out hydrogen protons. It's also used to pump in amino acids. So it can do a lot of useful things. But remember, the sodium potassium pump is always pumping sodium out. This is going to become super important, because if you eat too much dietary sodium, you will start to dissipate this gradient and you will get more sodium inside the cell. Now, because you have less of a sodium gradient, you're going to be less able to pump out your calcium. And with your vascular smooth muscle cells, they're going to stay chronically, instead of being wide open, the vessels is vasodilated. When those muscles contract, you shrink the diameter of that artery, and that'll cause problems. Because you're shrinking the diameter of that artery, then let's say you just eaten a meal. Now, because that artery is contracted, you can't get the insulin into the artery. You can't get the glucose into the artery, let's say in one of your muscle cells. And because of that, you're going to have insulin resistance. So notice that in the context of vasoconstriction due to a high sodium diet, the insulin and the glucose can't get into the skeletal muscle capillaries, so you get insulin resistance and diabetes, hyperglycemia postprandial after eating, because you can't deliver the goods. You can't get the glucose and the insulin to that skeletal muscle cell because the arteries are constricted. It's like the 5-lane highway and only 1 lane is running. Okay, things are not going to get there on time. All right, so that is insulin resistance due to a delivery problem. Uric acid also is a vasoconstrictor and will also cause the same problem. Insulin resistance due to a delivery problem of insulin and glucose getting to the skeletal muscle. Because normally postprandial, at least about 70% or more of your glucose is going to go into your skeletal muscles, be stored as glycogen, for example. Okay. Okay, and this is what I was alluding to earlier. The potassium and the sodium must always be constant inside the cell, and they must be isoosmolar with the extracellular matrix. And that's because over 98% of the positively charged ions inside your cytoplasm are potassium and sodium. So they've got to always be the same amount. If you had more potassium and sodium together, more of both of them, then you'd be hyperosmolar essentially. Water always follows the ions. Water can easily come across that plasma membrane. The cell would burst, dead cell. So you can't have that. They're always maintained that way. So if one goes up, if potassium goes up, sodium must come down. If sodium goes up, potassium must come down. You need to know that. That's important, okay? To maintain the osmolality of a cell and a cell's volume, okay? You have to have that. That's why you really shouldn't talk about potassium and sodium as if they're different subjects, because they're always connected. There always are. There's no exceptions to that. And that's also why you hear all these people talking about sodium on the internet, and it doesn't quite make sense, and you hear people contradicting each other. And the reason is they're not talking about the K factor. The K factor is what matters. The K factor is the ratio of potassium to sodium. You have to know that. And Richard Moore, the best expert in the world on the subject, says you have to have a minimum K factor of 5 to prevent hypertension, meaning you must ingest from your diet at least 5 times more potassium than sodium. Okay. I made a video a couple days ago about what's the deal with sodium and potassium. And I go into this in more detail. Okay. And this is really the key secret of hypertension. Plant foods got potassium. P for plants, P for potassium. So just eat your plant foods and you'll get all the potassium you need. That's the big secret. What is everybody deficient in the Western population? They're deficient in the things that come from plants. They're low in potassium. They're low in magnesium. They're low in antioxidants. They're low in fiber, because all that stuff comes from plants. Those are the real deficiencies. But do you ever hear anybody ask about that? No. It's like all the ignoramus proles. They always say, what about good fats? What about protein? What about calcium? Those things are all irrelevant. You can't be too low in those things. They don't matter. What matters is these things, and how do you get them? You just eat your plants. Our ancestors probably ate about 20 times more potassium than sodium. Okay, and then this is something this lecture is really for beginners, so the experienced people know this already, but the bottom line is you win in every way with the low-fat vegan diet. Okay, you eat the American westernized diet, standard American diet, real high in fat, moderately high in sodium, moderately high in oils. You're screwed. Okay, you're going to get hypertension, you're going to get diabetes sooner or later. You're going to plug up all your arteries, have things like heart attacks, most common cause of death, significant risk of stroke, impotence, cancer. Okay, you're screwed. All right, the Japanese diet, sort of East Asian diet, also Korea and China, they did eat a low-fat diet. A lot of white rice, for example, is 85% of their calories in that ballpark. But what got them in trouble is they smoked like chimneys, and they had tons of sodium, like 12 to 14 grams per day. That's like 12,000 to 14,000 milligrams of sodium per day. And because of that, they got high blood pressure. The high blood pressure damaged the arteries in the brain. This is the Asian pattern of atherosclerosis, and they had a high rate of strokes. They were still relatively healthy, like those Japanese, especially in Okinawa, where they didn't put as much sodium in their food. But that's the deal with them. And they were some of the longest lived people in the world, like Okinawa. Okinawa is kind of like what Hawaii is to the United States. It's sort of just south of mainland Japan. South Asian people, like in India, what gets them in trouble is you see them and they all seem pretty skinny. They look pretty healthy. They'll tell you they're a vegetarian, but then you start hearing stories about them having diabetes and coronary artery disease. And what's getting them into trouble, they do eat a little bit of animal food in the form of ghee as their butter and some yogurt. But what really gets them into trouble is they have, and they also have, a lot of them are high in sodium, but what really gets them in trouble is they eat a lot of fried food. And that's sort of like the secret thing that makes people eating an Indian diet sick. So that's why they get a lot of diabetes, and it's often type 1.5, adult onset autoimmune diabetes. And it's also because this goes back to Tetsumori Yamashima, MD, PhD from Japan, his calpain-cathepsin theory of toxic aldehydes from the metabolism of omega-6 cooking oils. The bottom line is they destroy the pancreatic beta cells. I've given other lectures about this in the past. And so then they're kind of screwed, because then they get diabetes, and that increases their hypertension and their risk of heart attack and stroke and cancer and all that other bad stuff. Low-fat, low-sodium vegan diet, you win in every way, okay? You keep your arteries open. You don't get diabetes. You don't get hypertension. You're unlikely to get autoimmune disease. Thus, you're unlikely to have atherosclerosis or to ever get a stroke, and you're much less risk of cancer. Why wouldn't you want that? You win in every way. It's like winning the jackpot, academic orgasm. Why wouldn't you want that? Of course you should want it. That's why I do it. I like people to be nice to animals. I respect religions like Seventh-day Adventists that want to eat vegan for religious reasons, and Pythagoras, the Pythagorean diet it used to be called. But I just do it for health. Okay? If I could become 18 years old again by eating the meat, I would do it. But it doesn't work. It makes you sick and it accelerates your aging. Okay? Now here is normal insulin sensitivity. Insulin after a meal, postprandial, binds to the insulin receptor on the skeletal muscle cell. That sends a signal to the vesicles carrying the glucose type 4 transporters to travel from the cytoplasm up to the plasma membrane of the skeletal muscle cell. Then these channels for glucose type 4 transporters they're called, they merge with the plasma membrane and then they enable glucose to come into the cell. Okay? I like that Bruce Lipton summary of how a cell works. He talks about the plasma membrane being the brains of the cell. He says the nucleus is just the DNA, it's just the blueprints, okay? It's not the brain. The brain is the plasma membrane, and it's got all these sensors that are sensing the external environment, binding to hormones, binding to chemicals, and figuring out what's going on in the world. He says the DNA is really just sort of the hard drive with a bunch of different programs, and based on what's encountered in the environment, it's the plasma membrane that is the thinking part of the cell, and it sends a message to the DNA. Okay, make more of this protein, less of this protein, for example. So anyways, this is normal insulin sensitivity, getting the glucose type 4 transporters in skeletal muscle to go up to the plasma membrane so glucose can come into the cell postprandial, and that will lower the blood glucose level. This glucose, much of it will be used to make glycogen for that skeletal muscle. Okay, that's a key point. Oh, these glucose type 4 transporters are also present in brain cells. So that's why brain cells are also affected by insulin sensitivity. You need to know that. Exercise also is wonderful. Exercise will cause these glucose type 4 transporters to move up to the plasma membrane and allow glucose to come in. So somebody with diabetes, even type 1 diabetes, they can get a lot of benefit from exercise to get that glucose to come into the cells. Okay, now I'm going to show you something very interesting called the flip-flop maneuver of fatty acids. This comes from a paper by Anthony J. and James Hamilton. This is not the Anthony J. who talks about estrogenic chemicals, okay? He's a good guy on estrogenic chemicals, doesn't know that much about nutrition. But these two guys, Anthony J. James Hamilton, in 2020 wrote a paper here about how does fatty acids get across the plasma membrane. And what they figured out was they're not dependent on a transporter. Unlike the glucose, which must have the glucose type 4 transporters to get into the skeletal muscle cell, the fatty acids, they just come up to the outer leaflet of the plasma membrane on a skeletal muscle cell. They become protonated, which enables them to intercalate into the outer leaflet of the plasma membrane, the outer face of the plasma membrane, and then they flip-flop into the inner leaflet, and then they come into the cytoplasm. The significance of this is there's no transporter that you can inhibit, and the cell cannot control the rate of their entry. It's simply proportional to their concentration in the blood, so that's called constitutive. And so what that means is the more fat you eat, the more fat gets into your skeletal muscle cell. Well, guess what? The more fat gets into your skeletal muscle cell, the more insulin resistance you have. So, the smart move, the only way to win this game is eat less dietary fat. That's the main thing that causes insulin resistance is excessive dietary fat, especially saturated fat, okay? And this is why the fat gets into the skeletal muscle faster than the glucose does. And it gets into the mitochondria too rapidly and it overwhelms the mitochondria, something called overnutrition. Okay, I'll show you on the next slide how this works to cause insulin resistance. Well, first of all, it's going to inhibit intermitochondrial membrane electron transport in the region of coenzyme Q and complex 3. And then electron transport is going to start to back up. So it's like you basically blocked off the highway, and now things start running backwards, looking for a detour. But this is going to cause a backup of electron transport. You're going to start dropping electrons down onto oxygen in the matrix of the mitochondria. That's going to generate free radicals called superoxide anions, and then you're going to try to neutralize them with superoxide dismutase. And you can do that to a large degree, but there comes a point when you make too many of them, and then they start causing reactive oxygen species stress, oxidative stress in the mitochondria, and it's going to cause all kinds of problems in diabetes. We're not going to get into that all right now. I can tell you, if you want to learn more about this, look at the Michael Brownlee paper. It's a masterpiece, the Sistine Chapel of medical research papers. Okay, now here's how insulin resistance works. You've now got this overnutrition effect whereby the mitochondria is overwhelmed by all the fat. It's sending too many electron carriers up to the inner mitochondrial membrane with NADH. Too many protons too quickly are pumped into the intermembranous space between the inner and the outer mitochondrial membrane. It says we can't pump anymore against this gradient. The gradient has gone too high, and electron transport starts to reverse, and you start dropping them down into the matrix. Okay, but the mitochondria knows there's a problem. It's like, whoa, overnutrition. I cannot handle any more energy coming into the cell. Send a message to the cytoplasm. stop with the glucose type 4 transporters. The glucose type 4 transporters are blocked from going up to the plasma membrane. So the glucose is stuck into the blood, and you get high blood levels of glucose, hyperglycemia. That's what insulin resistance is all about. The pancreas will respond by making more insulin, so you'll get high levels of insulin in the blood, hyperinsulinemia. But this concept of overnutrition is very important. And postprandial, it's due to excessive fat getting into the skeletal muscle. It's called intramyocellular lipid. The hyperglycemia, though, can go to other locations like endothelial cells, the retina cells, the kidneys, the peripheral nerves. And that's why you can get diabetic retinopathy, diabetic nephropathy of the kidneys, peripheral vascular, microvasculopathy, because those other cells are constituted for their uptake of glucose. They don't have glucose type 4 transporters, so they can become overwhelmed by too much glucose coming into those cells. But this is where it all starts, in the skeletal muscle. The earliest detectable finding of insulin resistance is fat accumulation in skeletal muscle cells. And the guy who figured this out in particular was Gerald Shulman, definitively was Gerald Shulman, by putting an electron, a nuclear magnetic resonance spectroscopy type of microscope equivalent on top of the cell to measure that's what's happening. Okay, so it's been proven. They've known that fat is what causes insulin resistance going back to 1927 and the J. Shirley Sweeney study, but now they more precisely know, more definitively know. Okay, we talked about the fat stages of diabetes. I sort of made up these fats based on the Shulman theory of ectopic fat. First, you get too much fat in your skeletal muscle, so you get postprandial hyperglycemia. Then you get too much fat in your liver, and it can't sense the blood glucose levels accurately, so you get fasting hyperglycemia, because the liver doesn't know when to shut off sending glucose into the blood. It keeps on breaking down glycogen. It keeps on running gluconeogenesis, even when blood sugar levels are high. The liver's main job is to provide adequate blood glucose to the brain during the fasting phase. Okay, then you start accumulating fat in the pancreas. You get fatty atrophy of the pancreas, and you lose the beta cells, and now the patient's basically screwed. They're insulin dependent, okay, and it's become irreversible. So the sooner you treat type 2 diabetes, the better chance you got to completely reverse it. And then the locations where you had constitutive uptake of glucose, because the cell part is always on for the most part, things like the endothelium of the arteries, all right? So you get diabetic retinopathy, diabetic nephropathy, peripheral neuropathy, okay? If you can get the patient to lose weight, their fatty liver will go away. Fatty liver is like prediabetes, diabetes of the liver. And this guy, Roy Taylor, showed, he won the Banting Award 2012 by getting people to lose about 30 pounds of weight or more in these fat diabetics. Their fatty liver went away. It's the first spot you lose the fat from. And they were all cured of type 2 diabetes. So it's pretty easy to cure a person with type 2 diabetes. Just get them to lose 30 pounds of weight or more. Switch to a low-fat vegan diet. Okay, so anyways, that's 2012 Banting Award winner. Shulman won the award in 2018. Michael Brownlee won it in 2004. The best diabetes researchers in the world. So anyways, I hope you found that interesting and useful.